Welcome back. I hope you had a great weekend. Let's get started with a new chapter. Chapter 6, Sampling and Sampling Distributions. As researchers, we rarely have enough time or money to collect information about an entire population that we're interested in. So if we're interested in how students at our college feel about a certain topic, there's no way that we have the resources to ask everybody, even if it's a small community college. But what we can do is take a representative sample of that population in order to say something about the entire population. You probably heard that before, that they say, oh, Americans feel about this and this topic a certain way. And you might go, nobody asked me. How can they make that assumption about the entire population of Americans when nobody asked me? So they might have taken a random sample of the population and asked them a specific question. And from that sample, based on the information from that sample, they made inferences about what the entire population thinks. And this is all based on sampling and sampling distribution. So let's begin with chapter 6. After this chapter, you will be able to describe the aims of sampling and basic principles of probability. You will be able to explain the relationship between a sample and a population. You can identify and apply different sampling designs. You will be able to apply the concept of the sampling distribution and also describe the central limit theorem. A population is defined as a group that includes all the cases in which the researcher is interested. So this can include individuals or objects or groups. A sample is a relatively small subset from a population. A population, for example, could be all students at the community college that you're interested in. Or it could be everybody in California. So the population would be everybody in California, but we would just take a small subset from that population. So take maybe a sample of 100 people from California and then ask them a specific question. When we talk about the data that represents either a population or a sample, they have different terms. A parameter is a measure, it could be, for example, a mean or a standard deviation, that is used to describe a population distribution. So parameter goes with population. A statistic is a measure, again, for example, mean or standard deviation, that is used to describe a sample distribution. These terms are really easy to remember. Statistic goes with sample, parameter goes with population. The notations for the sample and for the population are different, and we have to make sure that we distinguish, are we talking about a sample or are we talking about a population? When we talk about a sample mean, we use y hat. If we talk about a population mean, we use the lowercase Greek symbol mu. When we talk about proportions, the sample notation is p, and for the population, we use the lowercase Greek symbol again, pi. The standard deviation is notated for the sample with an s, and for the population, again, a lowercase Greek symbol, sigma. And the variance is just s squared for the sample, or sigma squared when we talk about the population. The distinction between a sample and a population is a very important one in statistics, and it's really important for the formulas later. So here's a visual one more time. Here we have the population, or the group that includes all the cases that we are interested in as a researcher. And then we take a sample from that, which is just a subset of cases selected from the population. A statistic is the measure that is used to describe the sample distribution, and the parameter is the measure that is used to describe the population distribution. Probability is a quantitative measure that a particular event will occur. We really use the concept of probability all the time. For example, you might ask questions like, how likely is it that I'm going to get an A on this exam? What is the chance that my sports team is going to beat the other team this weekend? What is the chance of rain today? But in everyday conversation, the answers are always kind of vague, right? Probably, pretty much, very unlikely. With probability theory, we can offer far more precise answers. So we can say there's an 80% chance that our sports team is going to win this week. There's a 70% chance that I'm going to get an A on this test, and so on. And remember the research process I showed you in the first lecture. Research begins with a question about an entire population. Actual research is always conducted using a sample because, again, we don't have enough money or enough time or enough resources to get the information from everyone in the population. Inferential statistics uses sample data to answer questions about the population. And with probability, we are able to determine what kind of samples we are getting from the population. So probability allows us to establish a relationship between samples and the population, because probability is a measure of how likely it is that a given event or behavior will happen. Let's look at this in more detail on the next slide. Probability, we said, is a quantitative measure that a particular event will occur. Several different outcomes are possible. Probability is measured in terms of numbers between 0 and 1. If the probability is 0, it means that the event will never happen. If the probability is 1, it means the event will definitely happen. If the number is in between, it may happen. The closer the number is to 1, the more likely it is that this event is going to happen. Probability is mutually exclusive, meaning that two events cannot occur simultaneously, so they cannot happen at the same time. If there is a chance that A will happen, B cannot happen. And the probability of any specific outcome is a fraction or a proportion of all the possible outcomes. The formula for probability is the probability of A happening equals the number of outcomes that are classified as A over the total number of possible outcomes. This sounds a lot more complicated than it actually is. Let me show you an example of probability. Assume I give you this question that I usually give in my introduction to sociology class. Which of the following men is generally known as the father of sociology? So he's the one that came up with the term sociology. Well, if there are 4 possible answers in a multiple choice question, and you don't have a clue about what the answer is, then the probability of getting it correct, because we know there's one correct answer, is the number of outcomes that are classified as A, so as correct answers, we know that's 1, over the total number of possible outcomes, and there are 4 choices. So the probability of getting it correct is 1 over 4. So the probability is 0.25. Let's look at another example of flipping a coin. So when you flip a single coin, what is the probability of getting tails? The probability is 1 over 2, because we know that there is 1 tail and a coin has 2 sides. So the probability is 0.50, 50-50, right? Let's do another example. Let's say we have a well-shuffled deck of 52 playing cards, and we want to know the probability of drawing a king. By the formula, we know the probability of getting a king is 4 over 52, because we know there are 4 kings in the deck and there are 52 cards. The probability of drawing a king is 0.0769. What is the probability of drawing a heart? You know every deck has 4 suits, so the probability of drawing a heart is 13 over, again, the total number of cards, 52, so the probability of drawing a heart is 0.25. Probability sampling is a method of sampling that enables the researcher to specify for each case in the population the probability of its inclusion in the sample. And we will be talking about 3 different probability sampling. The first one is the simple random sample. And that is a sample designed in such a way to ensure that every member of the population has an equal chance of being chosen, and also that every combination of n members has an equal chance of being chosen. What's important is that the probability of being selected needs to stay constant from one selection to the next when more than one individual is selected, and this requires sampling with replacement. And it's really simple again. It just means, let's say I have a class of 30 students and I want to take a random sample of 5 students, and I pick my very first student and say, come up to the front of the class. This student had a chance in 1 in 30 to be selected. Well, if he stays in front of the class now, Now the next student has a chance in 1 in 29. So in theory, I should throw him back into the class and then take another sample. So the probability of being selected always stays 1 in 30 and not 1 in 29. And then if I chose my second one, 1 in 28, because then the probability increases of being selected because the number of people actually gets smaller. That's what's called sampling with replacement. The next one is a systematic random sample. And that is a method of sampling in which every so many member, so the book refers to this as kth member, in the total population is chosen for inclusion in the sample after the first member of the sample is selected at random from among the first k members in the population. Let's assume we have a population of 1,500 and we want to have a sample of 500. So we divide 15,000 divided by 500 and we get k as 30. So now we would choose our first student at random and then we would select every 30th student after that until we reach our 500, our sample that we want. Stratified random sample is another probability sampling. And that's a method of sampling obtained by dividing the population into subgroups that are based on one or more variable that we are interested in, and then drawing a simple random sample from each of the subgroups. So for example, a subgroup could be based on race or ethnicity or some variable that you find of interest. So you would divide the population into the specific racial or ethnic group, and then you would draw a simple random sample from the different groups. In a proportionate stratified sample, the size of the sample selected from each subgroup would be proportional to the size of the subgroup in the entire population, and in a disproportionate stratified sample, the size of the sample selected from each subgroup is deliberately made disproportional to the size of that subgroup in the population. The sampling distribution is the theoretical distribution of all possible sample values for the statistic in which we are interested. Let's assume we take multiple samples from a population. So we choose 35 people randomly, we observe how many, for example, sit-ups they can do in 5 minutes, then we add the sit-ups together and then divide them by 35 and get the mean for this first sample. Let's say the mean is 25. Then we take another sample. Again, we choose 35 people. Most likely they are different people from the population we are interested on. Again, observe how many sit-ups they can do in 5 minutes. We add all the sit-ups together from this group and then we divide them by the 35 and then get the mean for the second sample. And let's say that is 20. Now we take another sample, so sample 3, again, choosing 35 people, observe how many sit-ups they can do in 5 minutes, add all the sit-ups from this group together, divide them by 35, and get the mean for the third one. Let's say that's 19. So let's say we do this 20 times. So we take 20 samples of 35 people each and always get the mean for each sample. If we take several samples, all the same size from one population, the samples will obviously have different means. So some samples were going to be above the population mean and some are going to be below. The distribution of sample mean states that if all samples are the same size, then the mean of the sample means will equal the population mean. You can see here that the samples differ from each other. So we have a mean of 25, a mean of 21, a mean of 20, 19, and so on. So the samples differ from each other. Given a random sample, it is unlikely that sample mean would always be the same. So the sample means always differ a little from each other. And the distribution of sample means is the collection of sample means for all the possible random samples of a particular size that can be obtained from a population. And you can see if we sum up all the means and then take the mean of the means, we come up in this case of 22.4. That is the mean of the means. The sampling distribution of the mean, therefore, is a theoretical probability distribution of sample means that would be obtained by drawing from the population all possible samples of the same size. In reality, we obviously don't take hundreds of samples just in order to generalize to the population. We normally only take 1 or maybe 2 samples. However, we can still derive a standard deviation of a theoretical sampling distribution as if we would do all these samples. And that's what's called the standard error of the mean, or sampling error. It describes how much dispersion there is in the sampling distribution of the mean. So error doesn't mean we made a mistake, but it is the natural discrepancy or the amount of error between a sample statistic and its corresponding population parameter. Because again, two samples are very, very rarely identical. These properties of the sampling distribution of the mean that we just talked about are summarized systematically in one of the most important statistical principles that underlie statistical inferences. And that's what's called the central limit theorem. It states that if all possible random samples of size n are drawn from a population with a mean and a standard deviation, then as n becomes larger, the sample distribution of sample means becomes approximately normal, with the sampling distribution of mean equal to the population mean and the standard deviation equal to the sampling distribution of the mean standard deviation. This is significant. Because of the central limit theorem, we know that with a sufficient sample size, the sampling distribution of the means will be normal, regardless of what the original shape of the population distribution is. Therefore, even when the population distribution is skewed, we can still assume that the sampling distribution of the means is going to be normal, as long as n is large enough. In conclusion, the central limit theorem notes the larger the size of the sample, the more closely the sample statistic cluster around the population parameter, and with sufficient sample size, the sampling distribution of the mean will be normal, regardless of the shape of the population distribution. Here's a summary of the key terms for this chapter.